shear.
Sure.
Okay, we can figure out where that's going to occur. So that's how we would act if we were going to step through and truly figure out that compression zone. That's what we would look at. We'd essentially turn it back into a simple beam and run shear calculations on it. Okay, so we also up here, since we have our percentage of steel, we'll call that rho, right? We could say then that the area of steel equals rho times B times D, right? If the percentage of steel equals the total area of steel divided by the quantity of the depth and the width, the area of the steel is the same as the percentage times the area, right?
Beautiful handwriting.
Everyone agree with that?
Amazing. Yes.
Generally? We could also rewrite this as rho BD, yield strength times 0.85 F prime CB. Okay? What happens with this equation? What falls out of this equation? Our beam width would fall out, right? So that's another way that we can determine the depth of that compression zone. If we know our percentage of steel and the depth of our beam, along with our yield strength and our concrete design strength. Okay? The book then also gives you values for, if we rewrite this as A over D, and all that A over D is going to be is just your rho value, your percentage of steel, oops, sorry, D out, times our yield strength divided by F prime C, and B's out of there. Okay, so this is how you can check those numbers to figure out percentage of steel if you need, given your A over D value, which is in, I think it's table 13.3 on page 132? It might be 13.4, I forgot to write down what table that was. Oh, no, I'm sorry, I did write that table number. Table 13.2. I don't have the page number.
406.
406? Okay. So, the types of problems, there'll be two types of problems. We'll look at given
406 is 13 too.
beam dimensions, how much steel, and given given width, size, depth, and determine steel. Okay? So I bet you want to look at an example, don't you?
Not at all.
Not at all?
This is bush league.
I think that's a good stop.
Had your Wheaties this morning, didn't you, Ben?
I did.
Yeah, what the hell? What happened to the stomach ache?
Well, start talking about concrete, it just revitalizes me. What can I say? Okay, so
Banking on you ending early, you just wrote a whole book, man.
that's only like 3 or 4 pages. So example 1.
I'm gonna write this down.
I have burned through this whole notepad in just this class, man.
Okay, we've determined bending moments for a beam. We know a dead moment and we know a live moment. Okay, our dead moment is 58 kip feet,
Oh, yeah.
or how many pounds, how many foot-pounds?
58,000.
58,000, right?
Sure.
Our live is 38 kip feet, okay? So when we were doing bending moments, when we were doing shear, when we were doing axial, we were ignoring whether we were looking at self-weight of the beam, we were ignoring whether we were looking at live loads, we were just determining a bending moment, right? Okay, so here we've gone and we've determined that due to the weight of the structure itself, we have 58 kip feet of bending, and due to how we're loading the structure, we have 38 kip feet of bending. Okay, does everybody see where that's coming from? Okay. So, because of our construction conditions, our width is proposed at 10 inches. Our F prime C, so our design strength of our concrete, is going to be 3,000 psi, and we're going to use grade 60 steel, sorry, not grade 50 steel. Okay, so 60 KSI. What we need to determine what is our beam depth and area of steel. Then we'll look at size and number of bars. Okay? If we think back, way back to chapter 1, we talked about loading conditions, right? When we have these numbers, to design safely, we want to make sure that the combination of these two factors isn't going to over-exceed our capacity. So we need to determine our ultimate moment. And the ultimate moment for these types of conditions are 1.2 times our dead load, plus, and I'm sorry, we're in moments, so that needs to be a moment, plus 1.6 times the moment of our live load.
Why 1.2 and 1.6?
Those are the factors that structural engineers have come up with. So there's actually another term in here.
How are you gonna do that?
The moment for our roof load, but we're not dealing with a situation with a roof load here. Okay, so this term is 0. Okay. So what does this factor end up being? What is our ultimate moment? 1.2 times our 58, right? Plus 1.6 times our 38. Come out to be 130 kip feet. Okay. Remember those reductions from section 13.2? What do we need to use when we're looking at flexure? We're looking at bending. Be the same for flexure, tension, compression. Which number was it? 0.9, right?
Yeah.
Okay, so 130 divided by 0.9 gives us 145 kip feet. Okay? Since we're going to be working in inches, we want to convert this to inches as well. Okay? So I'll multiply it by 12 inches per 1 foot. Okay, so M sub T equals 1,739 kip inches. Okay? If you look at table 13.2, Our row value is going to be 0.0252. Sorry, I should say, so table 13.2, you see how it's, you've got two columns, one for 40 KSI, one for 60 KSI. And then you've got your various strengths, 3,000, 4,000, 5,000, 6,000. We'll always use 3,000, 4,000, 5,000, 6,000. However, in the real world, if we were using a mix of 4,300, 4,500, we just interpolate those numbers to come up with what these factors
Is
would be.
that T the tension, the moment? of
Yes.
tension?
Yep. Yep. We have an A over D of 0.592. And we have R value of 1.063 KSI. Okay? So, first thing we can rewrite, oh, I dropped that portion, didn't I? I missed the section where we talk about R. Should we go back and talk about R, or are you fine just using that number? Or do you want to see where it's derived from?
I'm cool with it.
Good to just keep on driving?
I'm still
Okay.
trying to write down the earlier stuff, so you can slow down.
Okay.
So you got the percentage. How'd you come up with that?
These values are from table 13.2.
Okay.
Okay, so no calculation, we're pulling that right out of the book. Okay?
So why'd you use that value out of the table though? Okay. 3,000
PSI design strength, 60 KSI yield strength on our steel. Okay?
So I see where it has it has more than, so all of these are for 60,
Correct.
but how do you know?
Because your F prime C is in KSI, right?
Yeah,
So your 3,000 PSI becomes 3.
okay.
Okay, does that make sense?
Yeah.
So your first selection is, are you working with grade 40 steel or grade 60 steel? Okay, we've got grade 60 steel,
And then just
then look
convert
at,
that over 'cause
Yep.
of the kit.
yep, 3,000 becomes 3, 2,000 becomes
I hate
2.
these kit. I'm gonna do the end.
Okay, so we also know that we can rewrite the moment of our tension as R times the width of the beam times the square of the depth. Okay? Out of these four factors, which one do we not know?
D.
We don't know D, right? So if we manipulate our equation, we can solve and determine our D. What does the D represent?
Where the R.
What's that?
Oh, you're saying like what?
Well, yeah, not necessarily from the equation standpoint. When we think back to what our beam looks like,
What the compression distance?
not the compression distance, it's the distance from the face of the beam to, what'd you say, Kyle?
Vertical distance.
It's the vertical distance from the top of the beam to the center of the steel. Okay? So as Justin said, we can rewrite this. So D is going to equal the square root of M sub T over B times R. Okay?
Is that
So your MT equals RBD squared or D squared?
RB D squared, sorry.
how did you?
So you divided D.
So we got R.
R is just
I
taking.
get R. I get where we got R from
Got
the
it.
table. I'm trying to figure out where did you come up with MT equals that equation?
So MT is just, remember that when we said our general equation, MT equals
T times D,
AS
AS
FY D minus A over 2,
Yeah,
okay? If we jumble a bunch of this stuff around, that's at row BD, and we can, or I'm sorry, row over BD. We can pull a D out of here.
so you get D squared.
Well, the D goes away.
Oh.
The D is reduced,
Yeah.
right? Then we need to, rewrite it. Oh, no, I don't need it. Sorry, I don't need the MT equation, I need the A equation. Sorry.
I agree.
I concur with that statement.
This is brutal.
Yeah, I got lost here on when I skipped this over.
That makes me feel really confident in doing
Yeah.
that.
It's about that time.
What's that?
We'll pick this back up on Tuesday. Oh,
But remember that you know these three values, right?
yeah.
So you can figure out your depth of your beam. Your depth of your beam is going to be 12.8 inches. Okay?
So D
Can you
equals,
Yep,
D equals 12.8.
yep.
That down.
D equals 12.8. Okay, we'll pick up there on Tuesday.
Have a good weekend, Ben.
You as well. I'll get this posted for you.
Easy.